change to define periods that they contain these L values. Yeah, so there should be an independent definition of this, and this I will give you now. And let's talk about these periods. And periods is something many of you have seen maybe already. So let me go to the following situation. We consider a compact Riemann surface. And to fix ideal, let's say the genus is G. Yeah. Bigger or equal to 0. And then it's known that this is in fact an algebraic variety. So this can be defined locally by polynomial equation. That's a very deep theorem resulting from Riemann-Roch here. And so our variety looks like this. Yeah, compact Riemann surfaces have some G holes. And now what we consider is we consider certain paths, gamma, on this Riemann surface. So gamma is a closed path. And then we have the pi1 of x. This is the fundamental group, which you can see also as the group of homotopy classes of closed paths. This means you just consider the closed path up to continuous deformation along your Riemann surface. And on the other hand, you can consider, yeah, this is a complex manifold. This has a complex structure. So one can say what holomorphic differential forms are, holomorphic one forms. Holomorphic one forms. And this is a complex vector space. And the dimension is equal to G if the surface has genus G. And now there is a pairing, usually referred to as a period pairing. And this associates to each some path and each differential form just a complex number, yeah, by integrating the form over this path. Yeah, this is usual path integral, which you also use in complex analysis. Yeah, that's a period pairing. And this induces, I write this a little bit differently, this induces a map, of course, because it's a pairing, to the dual space of these differential forms. So this is a dual C vector space. And the image of this has a name, and it's called the period lattice. So the image is the period lattice. Lambda of x. Yeah, this sits inside omega 1 of x dual. So this is a C vector space. And this is a subgroup which is free, generated by 2G generators inside here. Yeah. And then in this theory of Riemann surfaces, an important invariant is the so-called Jacobian variety, J of x, which is you take the quotient, which is then, yeah, this is isomorphic to 2G circles, product of 2G circles as a real manifold, but this has a complex manifold structure. And even more is true, this is also an algebraic variety. And in fact, with a group structure, so it's an abelian variety. And this is called the Jacobian. Okay, let me give an example here, which is somehow related to the introduction. So let's consider E, and this is defined by the following algebraic equation: 4 times x to the 3 minus 4x. And this is an algebraic polynomial in two variables, and it's a single equation. So this gives an algebraic variety. The solutions of this give rise to an algebraic variety in projective space, P2 of C, complex valued points. So this is a Riemann surface. So EC, I say the complex solutions are a Riemann surface of genus 1. It's called also an elliptic curve. And one checks that if you write down the following form, dx over y, this gives a holomorphic differential of one form. And now I can consider somehow the periods here, and then I can identify the period lattice of this. So lambda of E, this is given by omega times z plus iz, and omega is just the omega. This is the period lattice. And omega is just the omega we had before. So this is the integral from 0 to 1 of dt over square root t to the 4 minus 1. Yeah, and that's now an easy exercise in calculus, because you somehow express y in terms of x, and then you do some stupid substitution to get at this integral. Yeah. So, and then you check that this is somehow, you have in fact to compute two periods here, but they are given just by I times this omega and omega. Okay, moreover, no space here. So we see this omega appears here, and the omega appears really as a period as in this theory of Riemann surfaces. And this was the omega which appeared also in this sum, which was evaluated by Gauss. So moreover, we have the following. So the EC, this Riemann surface, that in fact its own Jacobian, and so the EC is really isomorphic to C divided by omega plus this lattice. Yeah? So this is, you can really understand this Riemann surface very well. So how to define now periods? What we have is a period lattice, but we just want to have one number. And so I have to explain this to you. And this is something which somehow underlies all this theory, because so far we were dealing with just complex Riemann surfaces, but somehow I want to do number theory, and this means I want to take into account that this is an algebraic variety, which should be able to be defined over a number field so that I can do some arithmetic with it. And so this I have to assume now. And so we want to say how to define the periods. And this we do as follows. So just to fix ideas, of course, everything can be made much more general. To fix ideas, assume that this algebraic variety X, yeah, this we know for abstract reasons, but we assume that it can be given locally by polynomial equations with rational coefficients. Yeah, so X is somehow the complex solution to an X0, and solutions, and X0 is an algebraic variety defined over Q. Yeah, so this means the defined by polynomial equations with Q coefficients. Okay, this should be good enough to do number theory. And then it turns out that there is more structure here. So if we look at the differential forms on X, these can be, in fact, generated, this vector space, G-dimensional vector space of the differential holomorphic one forms can be generated by algebraic one forms. Yeah? That's not trivial. So that can be generated by algebraic one forms. And these are algebraic one forms. And these algebraic one forms, this is a Q vector space of dimension, again, G. And if you extend the coefficients to C, then you get back the holomorphic forms. So this complex vector space is somehow given with a Q structure in the sense that we identify in some canonical way a Q-dimensional, a G-dimensional Q subspace. Yeah? That gives it an extra structure. And I have to say a little bit more. And somehow, now because we are working with the complex field, so complex conjugation, which I strangely enough denote by F infinity, because for us it's the infinite Frobenius, this acts on the solution space X0 of C just by conjugating the coefficients. Yeah, this is, if you think about it, you have somehow some polynomial with rational coefficients, and you have a solution over the complex numbers. You conjugate this solution, you get again a solution. Yeah, so this is because the coefficients are fixed under the complex conjugation. Yeah, this acts on this, and then I can do the following. Questions? No. I didn't get it. This should be smooth and proper here. Yeah. This, for the experts, this is smooth and proper. I mean, you can even forget about proper, but this is all technical. Yeah, and the rest can ignore these adjectives here. Yeah. Okay, and now we look at the following. So we have this injection. So this is the period lattice, and this sits inside the holomorphic forms. But now we consider this as something. So we have this Q vector space, and we don't want to extend it anymore to the complex field. We just want to consider the R vector space, the real vector space, which is generated by this basis. Yeah, fix a basis here, and then you get a real vector space here. And here I do the following. I consider this also as a real vector space. R. Yeah, this gives everything. But then I consider the fixed points under complex conjugation here. Yeah, this acts also on this lattice. It acts on everything here. Yeah, and this map turns out to be an isomorphism. Let us call this maybe C plus here, and then I define the periods as follows. So the periods lambda of x. This is just, I take the determinant of this map C plus. And what does that mean? So you take this with respect to a basis. So this turns out to be G-dimensional R vector space, and this is the G-dimensional R vector space. A basis in lambda x and omega 1 x0 q respectively. And this is then only well defined up to some invertible rational number. Yeah. So because if you change the basis here, then you get, and you take the determinant, then you multiply by some rational number, and the same happens here. Yeah. So it's not the number which is well defined on the nose. But if you think back somehow to the pattern we had, so we wanted to say the L function is something like period times rational number. Yeah, and if we're just interested in that statement, then we don't have to fix, we don't have to be so careful about this rational number. Yeah, only if we want to do more precise considerations. But this is somehow another story. And that's a really very complicated story. Let's stick to this case. So we have this periods. So this is the period of, say, this lattice, lambda x. And now just to give you an idea, I do a little aside, which not everybody has to follow here. But if you want to see, I mean, we're talking about Riemann surfaces here, but this should be a general story for all, really for all algebraic varieties. And how does one proceed there? Just to give you an idea what kind of things come in. So let now be x0, will be short. X0, any algebraic variety. And I'm not so precise about smooth and proper here because everything is even more complicated in reality, and I can ignore these questions really. To understand what comes in, this suffices. The point is then that if I look at the associated complex variety, so suppose this is really smooth and proper, so then x0, the solution space, this is a smooth complex variety, smooth compact C variety, C manifold, complex manifold. And this complex manifold, this has, if you study it from a topological viewpoint, you have singular cohomology groups. Singular cohomology groups here. And on the other hand, you have always this algebraic differential forms, and you can consider the algebraic de Rham cohomology, yeah, which is defined similarly as in the complex case. So in the complex world, you say not one, it's I. So yeah, so in the complex case, you would say you take the closed differential forms divided by the exact ones, and this gives you a vector space which measures somehow how far a differential form is from being integrable on this manifold. And here, the algebraic definition is a little bit more technical, but it's essentially the same. And it turns out, as is in the case of manifolds, this is a very basic thing there, that if you extend coefficients to the complex numbers, you get so-called comparison isomorphism, yeah, which is theorem of de Rham. And now you do essentially somehow, this replaces the period lattice, this replaces the differential forms. And I only say the following because this introduces a notion which comes up later. So consider for any integer z, the following map, c plus n. And this goes now from this group. So you have, again, somehow an action of complex conjugation, but now you take an eigenspace, so where complex conjugation acts either, so it decomposes in two eigenspaces essentially, if I take real coefficients, but never mind. And on the one space, it acts by +1, and on the other space, it acts by -1. I take this one, this eigenspace, and then I consider it as a real vector space, and then I have a map to this algebraic forms. And then you have to divide by the nth step of the Hodge filtration, which is another important invariant of the complex manifold. And so sorry, I have to first tensor with, no, like this tensor with R. And now this map is not always an isomorphism, but in the case it is, the linear says I call that algebraic variety critical. Sorry? This is the Hodge filtration, sorry. This is the Hodge filtration. Hodge filtration. So this is, you can define this somehow algebraically here. So you know the Hodge decomposition of complex manifolds. So you can, if you have a compact, smooth C manifold, then you get finer structure on your cohomology, and by decomposing this into spaces where you have P holomorphic differentials and Q anti-holomorphic differentials, and you have harmonic coefficients, yeah, and then if you get the Hodge filtration by summing over all P and Q such that P is bigger N. Yeah, that's called the Hodge filtration. So that's an invariant of that manner. It's unbelievably complicated. We had wanted to talk about simple series, but that's how it is. Yeah. So, okay. But I wanted to define this notion critical because this will be an condition later. So the linear says this is critical if this C plus n is an isomorphism of real vector space. Yeah. So, and then if I have that, I can define in general the period. And this is defined to be 2 pi I to the n times again the determinant of this C plus n. And again, with respect to the basis taken here and here. Yeah? So it is well defined up to rational numbers. So now that aside is over, but now I can tell you something which is related to the examples we had in the beginning. Namely, let's consider the variety which is just a point. Yeah, we write it this way. This is just a point consisting of one point defined over Q. And if you do this, you have not so much cohomology, but then the H0 space, this is critical if and only if, so for n bigger or equal to 0, if and only if n is odd, even. Wanted to say even. N is even. And this we will see later. So the period here is then 2 pi I to the 2k, and you have seen that number before. Okay. Oh my goodness, time is running. Now I have a very difficult task because I have to talk about L functions. And what are L functions? And it's not so easy to give you the precise idea here in general, but let me first give you an intuitive picture. So how do we think, we the arithmetic geometers, how do we think about a variety x over the integers? And we think somehow as being differential geometers. So we have here, we have z. I should maybe make this a little bit bigger. We have here z. And here we have the prime numbers, so 2, 3, 5, 7, and so on. And here we have a prime ideal, 0. And now this variety you should think of as something being fibered over that. So you have somehow a variety here. You have a more complicated variety here. You have something like this. Here you have maybe something like this. And here you should think of having something like a Riemann surface. That's how we think about this. Yeah. So there is a lot of information somehow. If this is something which is defined by polynomial equation with integer coefficients now, and now we have much more information. So we had for each prime, we have a variety. So this gives a variety x over the finite fields Fp. Yeah, Fp is the finite field with p elements. Okay. Now the L function, this consists of arithmetic information contained in here. And this arithmetic information is in a certain sense local. And what does that mean? Local? It means it is just concentrated in each fiber over P. So, and now I give now some examples before I give you the general definition. Yeah. So the first example is we do somehow the spread out point. So this is the trivial fibration over each prime ideal lives exactly this prime ideal. We call it spec Z. That's somehow the basic thing. What do we get? So this is now an infinite product, the L function, over all primes. And now comes the local factor. And what is the local factor here? It's 1 minus p to the minus s. And that's maybe something you have seen before, because this is the famous product decomposition of the Riemann zeta function. Yeah, so you can write it as a series 1 over s. This is also due to Euler, although he was always a little bit sloppy with his infinite products. And this is, of course, just the Riemann zeta function. Let me give you another example. Now we consider x0. This is spec of the following ring. So we take somehow we adjoin the f roots of unity. So theta f is a primitive f root of 1. So zeta f to the power f is an integer, is 1. And you take somehow all polynomials in this thing, and then you get a ring. And this ring is this ring. And I also take a character, chi, and I take a character from the following group. I take the integers modulo z to the f, and I take all elements in here which are invertible for multiplication. And this is an abelian group. One knows the structure very well. Of course, this is a fundamental theorem in algebra. And so you have, we are giving ourselves also such a character. Yeah. And then the L function is the following. We take the product p 1 over 1 minus, and now we take chi of p. We avoid the primes. So it's over all p, but we avoid the primes which divide f. And then we take p to the minus s. And this can be also developed into a series. And you get chi of n divided by n to the s. And that's usually called a Dirichlet layout series. Okay, let me give a specific examples here. Example for f equals to 4. So this group, this consists of exactly 2 elements, namely 1 and 3. These are the only invertible things. And we consider the following character to C star. So n in here, this goes to 1 if n is congruent to 1 modulo 4. And it goes to minus 1 if n is congruent to 3 mod 4. Yeah? So this we can do. And what we get here then as a Dirichlet L function is something we have seen before. This is the series n to infinity. And now you have minus 1 to the n minus 1 divided by 2n minus 1. And this is for this specific character, maybe I should give it a name, chi 0. This is the L value of chi 0 at 1. Yeah, so this series studied 500 years ago by Madara. This turns out to be a Dirichlet series here. So that's a typical L function. Questions? So, but we give another example, 3. Now we consider the ring where we adjoin just I, yeah, and this is just all complex numbers where real and imaginary part are just integers, and this is a ring, and it's even a principal ideal domain. One of the simplest rings you can. So unique factorization domain. So this implies the following. So whenever I take an ideal in this ring, ideal, which is congruent as coprime to 2, so this means coprime, 2 does not divide this ideal, then I can show that there exists an alpha, an algebraic number in that field, quotient field generated by this, such that the ideal A is really principal generated by that alpha. And alpha can also be taken to be congruent to 1 modulo 2 plus 2i. Okay. So that looks a little bit technical. But now we consider the following character. So rho goes from the group of ideals coprime to 2 to just this algebraic number field. And it does the following. So A goes simply to this alpha. Turns out that this is a character, and that's maybe the easiest example of a true Hecke character, although this is also a Hecke character, but that's a Hecke character. And then we can write down the L function here, and it has a similar shape, a little bit more complicated. Here we take the product over all prime ideals now in this ring, P prime and still coprime to 2. And now we do something which we have done all the time, which was so successful, we do it again. Yeah, so we take 1 minus chi of P times norm of P to the minus S. Yeah, and this is in fact again a series of the following shape. So it runs over all ideals in Zi coprime to 2. And you take 1 over, what do I wanted to write? Norm of, no, I wanted to write alpha to the 2 alpha to the S. So this I wanted to write. And this is called L rho of S. Yeah, that's somehow the L function. And this belongs to the Riemann surface, the elliptic curve, which we have seen in the beginning. So all these are now Hecke L functions. Sure. It has what? Not? Yeah, that's not true. Yeah. You see. Yeah, that's that's a very good question, but it leads us to a problem which I try to put a little bit under the rug here. Yeah, because you see, if you consider now this variety, this has a group action by the Galois group. Yeah, and the Galois group is this. Yeah, so this means that if you now consider the cohomology of that variety, it inherits such a group action. Yeah, and you can decompose now the cohomology after extending coefficients into eigenspaces for this action. And each eigenspace belongs to a character. So the cohomology of all that thing, yeah, this is a direct sum somehow of this situation. Yeah, and in this sense, the variety knows about all these characters. Yeah, but it's a very good question. Yeah, I mean it's not obvious. Yeah, but you see, to formulate a conjecture in general, you have, I mean, there is still more to do. Yeah, so if you want to consider such series, but yeah, I mean, this is because then, I mean, if you go up some tower here of number fields, then you get in deep trouble. What are really the varieties here? You can define it, but I mean, the finiteness questions and so on, this is more difficult. In a certain sense, I would say somehow, if you go to Iwasawa theory, then this is exactly the idea, that you consider families of these L functions. Maybe we go into this later when the audience is not anymore so general. Yeah, so that's because this is, I cannot explain too much about it now. Yeah? Oh, now I raise things at the wrong board because I was distracted. I'm sorry. I'll leave it like this. So we have seen now these examples which are related to the examples I started with. And now I have to beg your pardon that, again, there will be a little aside that you see a little bit clearer what I mean with this local information and which is encoded in this L function. So far, the local information was just that this is a certain Euler product. But I want to be a little bit more precise that you see what's really happening here. So a little other aside here, a little technical. It will end approximately here. Yeah, so don't worry. So we have a variety over Z, and we fix some prime number. Yeah, this means now we look just at one fiber. Yeah, over this prime. And I said this with one fiber, we have now a variety over a finite field. And what can we do? This is given by polynomial equation. And for each finite field, I can just look at the solutions of this polynomial equation over that finite field. It's a very classical operation which was known to the Greeks, essentially, that if you give yourself a Diophantine equation, so defined over the integers, then you reduce the equation modulo P and look at the solutions there. Yeah? And because this is a finite field, there are only finitely many solutions. I can count them. And I do this systematically. I do this not just for the field Fp, but also for all finite fields of P to the n elements. So this is defined to be the number of solutions of the equations given x0 over the field Fpn with P to the n elements. that's certainly a number theorists should be interested in. Yeah, there should be no doubt about this, that this is arithmetic information. And now we do the following. If you have such a sequence of numbers, there should be one reflex. You put it into a generating series. Let's do that. So I call this ZPX0T. And that's defined, it looks a little bit strange, but I don't explain why. But that's how it is. So we look at the following series, n equals 1 up to infinity. And now we take this number of solutions, fp to the n, times t to the n, and for some normalization reasons, we divide by n. This turns out to be a power series with rational coefficients in t. T is just a dummy parameter. Yeah, giving the generating series. Sorry? X naught. Thanks. Yeah, so I mean, if we allow more and more elements in our field, then we get more and more solutions, and we record them here. Yeah, so this generating series knows everything about these solutions, no doubt. Okay. And now we do the following. We define the zeta function of x0 as follows. So this is the product over all these local informations, x0. But now I have somehow get rid of this general parameter and introduce this complex parameter s. So I put p to the minus s here into this power series. But still, this power series somehow, as a formal power series in p to the s, still contains this information. And that's actually essentially already the L function. So that's what the L function contains, this information for all p's together. Yeah? So, and it turns out now, that's a very deep theorem, also due to the linear. So this is, namely, the Weyl conjecture says, proven by de Ligne in 1974. You can express this in the following way. I see I don't get it there. So I take the product I equals 0 up to 2 times the dimension of our variety. And then I take product over p, determinant of 1 minus the Frobenius at p inverse times p to the minus s. And this acts on a certain cohomology space, which is associated to x0. And I want to keep completely under the rug. This is difficult. And then I take minus 1 to the I plus 1 here. But if you see the shape here, this is somehow determinant of 1 minus something Frobenius acting on a vector space. And that's very similar, and given much more time and more technicalities, I could explain you how you arrive then at these characters here. Yeah, so that's somehow, for each I, this is the product of this L series. So this is the product of I equals 0, 2 dimension x0. And now I have to be careful. So there is somehow this HI space. This is encoded in this L function S. And I have here minus 1 to the I plus 1. Yeah, so all these L functions appear here, and put them all together, I get back somehow this local information about the variety. Okay. So yeah, that's maybe a good point just to reflect a little bit. But maybe before I do that, I state de Ligne's conjecture. So the aside was a little bit longer than promised, but it's over. And now I can state de Ligne's conjecture. So de Ligne's conjecture is now as follows. It simply says, so if we have such a variety over Z, that's a simplification, yeah, algebraic variety. I don't want to bother you with the technical details here. And it's such that the HI x0 is critical in the sense defined above. Yeah, that's a technical condition. But it's not always fulfilled. Yeah, this is like distinguishing between even Riemann zeta values and odd zeta values. The odd ones are not critical. Yeah, so there's no delinear conjecture there. There's a much more difficult conjecture there. Then we expect, or delinear says, we should expect the following. So the L value at n divided by the period of this thing, that should be always a rational number. Yeah. And now everything here is somehow seemingly well defined. Please. I did a mistake here. Don't ask these precise questions here, because I said I want to put the étale cohomology under the rug. Yeah, there is, so because there was a question, I have to answer it. This cohomology depends on a somehow auxiliary prime, which you have to choose L, but somehow these determinants are expected to be independent of L, and this is known in some cases, but it's wide open in general. Yeah. But for getting an idea, we can really suppress these technicalities. Okay. So I should say this, so because this was also asked, so there are variants, yeah, of this conjecture, variants for varieties over number fields and with coefficients, and in fact for motives, yeah, so I don't mention this, but this is really to get you an idea what this is about. So now you can ask, of course, why should we care about such a conjecture? Yeah, and of course there are many possible answers to this. I can give you my motivation somehow. In fact, for me, that's only the first step, because it turns out, and this is known in many cases, even in all examples I mentioned, that this rational number, this carries global information about the variety. Yeah, so this means the L function, this knows something about the fiber over each prime. But this rational number here, and that's completely mysterious, knows something about the global shape of this. Yeah. So, for example, yeah, but the Riemann zeta function, this, if you look at these integers, which are known, these are Bernoulli numbers. But there's an interpretation of these Bernoulli numbers which is completely unexpected. They have to do with the number of elements in the algebraic K-theory of the integers. Yeah, so that's a very global invariant of the integers. And this is known, and it's also known for the Dirichlet characters, and it's also known for the CM elliptic curves. This, sorry? Yes, you see. So somehow this, essentially, this is something like, so for the Riemann zeta function, you get something number of elements in the K1 of, not K1 of the integers. You have to look at the right n here. Yeah. So it should be K3 and so on. Yeah, number of elements there divided by number of elements in the accordingly even K-theory. And that's this rational number. In terms of the Riemann-Zeta function, that's true. Yeah. Yeah. So in general, you can express these invariants completely. And as I said, this is known for Riemann-Zeta functions. This is known for Dirichlet characters and for CM elliptic curves. I did this in my habilitation, actually. So that's a first step for me, but that's already something, because the period here, yeah, that's really interesting how this period, which is also a global information, is known by this L function. Yeah, that's also something very mysterious here. Yeah, there are many mysteries. Okay. Now I come somehow to the proper subject of my talk, namely, I want to point out what are these Hecke-L functions in general, and then I tell you what I will do a little bit, what we have done, and so on. Okay. So I have 20 minutes, is this right? Okay. So Hecke-L functions. And just some technicalities here, you can ignore it. This is now somehow the generalization of this third example, and there we had somehow these integers zi here, and this is now the ring of integers in a number field in some number field. And we have to fix some ideal OL here. And we consider, so a Hecke character is then a character from the group of ideals coprime to F to C star, yeah, as we had before. Let's give it a name, chi again. And this has to satisfy some technical conditions. Okay. And then we have associated the L series, L chi of S, yeah, which was, let me write down not the product, but this is somehow, sorry, this is, now you sum over the ideals norm of A to the S, and the ideals, they are still coprime to F. That's the shape of the series. And now, what is the relation to what I was talking about before? So what is somehow the algebraic variety which should underlie them? And that is conjectured to belong, and in many cases it's known, belong to abelian varieties with complex multiplication. With complex multiplication by OL. Okay. And the examples we had before, they were all of this shape. Yeah. So examples 1 to 3 are of this shape. Maybe I should be here precise. Belong either to abelian varieties or to H0 of a number field. But that's a known case somehow. So now I have to tell you something, because we had this condition here, and if we want to attack this conjecture, we better know which chi are critical here. And I don't want to give you technicalities, but I have to give you a fundamental distinction, because it will be somehow fundamental for all what I'm going to tell in the next lectures. So there's a fact. So chi can be critical only if either one of the two things is true, either the field L is totally real. This means all embeddings, field embeddings into C are in the real numbers, in fact. Yeah? Or L is totally complex, meaning no such embedding lands in R, and it has to contain and contains a so-called CM field, and that is just imaginary quadratic extension of a totally real field. Yeah, that's all technical. Don't worry. This is only preparing, because the ways of proof seem to be, at the moment, so before somehow we entered the subject, completely different. And I want to tell you in the next lecture that this is not the case, really. There's a uniform approach to both. But to discuss the known cases, I have to separate now between these two cases. So, and let me discuss the results here, a little bit chronological order, the linear conjecture for Hecker L series. So for L totally real, somehow the case L equals rational numbers, that's the easiest case. This was done by Euler, as we have seen, and in general, this was settled by Siegel and Kling. Klingen, yeah, in the 60s of the last century. And if L not contains a CM field but is a CM field, then there were first results by Damerel for the case L is an imaginary quadratic extension over Q. And then there was, in general, Shimura, so general for equal CM field. Shimura proved that the L value divided by a period is algebraic, and that this is somehow the right number here. It lives in the, I didn't tell you exactly in which algebraic numbers are allowed here. This was then done by Blasius, was a student of Shimura, and so proved then Delignier's conjecture. Yeah, periods are correct. Periods correct. You have to correct them, but he says how one gets it, and then you prove it. So the general case, L contains a CM field. There are some cases known, so by Colmes, and then also by Bergeron with different methods. So Colmes, this was in the 80s, and now Bergeron yeah, he proved that somehow this quotient is not just an algebraic number, but if you put the right periods here, you have to correct them slightly. Shimura don't get the right periods in the sense of Deligne. Blasius shows that you can correct them to get the right periods in the sense of delinear, and then that the algebraic number is the correct one as predicted by delinear. Yeah? So there was some little work to do after that was shown. Yeah? It's not so little, in fact. So it's very, very technical. Yeah? So in this case, so there were three authors, Colmace in the 80s and Bergeron, Charleroi. I hope this is correct. And Garcia, somehow around same time when our paper appeared, they treat the case L contains an imaginary quadratic field. So they are a little bit more general than Colmace. And the completely general case, this was then settled by myself with Johannes Sprang, former student of mine. And we proved again that this divided by periods is algebraic. And then 2 years after, my student Han und Kufner showed that Delignier's conjecture follows from this. Yeah, so that's the most difficult part. And then with Blasius' method, I mean, there are some very smart tricks in his thesis, so that's very great. But the hard part is this. Okay. So that's what is known. And I want to explain in the next lectures somehow how you can attack this, and also how one can attack somehow in a similar way both cases. Yeah. So, but let me say something, because my time. Let me say something why this has taken so long to complete this after this fundamental work of Shimura and Blasius. Well, this was somehow more than 40 years ago. And so what is the strategy of Shimura? So the strategy of Shimura is the following. So he relies on certain moduli spaces. So uses two things. First, so certain Eisenstein series plus their derivatives, they are related to these L functions, L chi of S, or these special values. I just put 0 here, but this is no restriction really. Yeah, that is known for this goes back to Hecke essentially, who also defined these characters in this generality for the first time. And now he uses the following somehow. So for L a CM field, the Eisenstein series define algebraic functions on an algebraic moduli space of abelian variety, varieties. And yeah, this Shimura was somehow the person who built up the theory of algebraicity of these moduli spaces with extra condition. And he realized that, of course, an algebraic function, yeah, this has to have algebraic values. And so this gives the algebraicity of his statement. Yeah? And the problem is and then he uses also plus algebraicity of the differential operators. This relies also on the algebraicity of this modelized space. The problem is both things fail badly in general. So strategy does not work like this. And I have no time to give you somehow the inspiration of our work, but maybe I can write down, I have 2 minutes, so I can get a formula. So there are two sources of inspiration. The first is that together with Sascha Behensen and André Levin, I had proved some years ago, I invented an approach to this Siegel-Klingman result and also to p-adic interpolation results in terms of cohomology, which will I explain tomorrow in my second lecture. And the other thing is that Banai and Kobayashi, should mention the names, Banai and Kobayashi, in 2010, they realized something which somehow was surprisingly overlooked for ages about theory of classical elliptic functions in the sense of all these people who have contributed to it, Kronecker and Eisenstein and so on, and André Weil. And they realized that if you write down the generating series of all these Eisenstein values, and this will be my last formula. So this is a generating series. And I will not define all terms, but we have a pi here, pi to the a times divided by a factorial. And then you have these Eisenstein numbers, which are we are interested in them because they should be related to L values. And here I have z to the minus a times w to the b. These are the variables. And this generating series, which could have been considered, always in this theory, this is an algebraic section of the Poincaré line bundle. P on the underlying elliptic curve, which is here somehow in the background. And this gives now, as good news, a way to avoid modelized spaces because you can work on this thing directly. The bad news is this doesn't generalize to abelian varieties in higher dimensions. You have to invent something else. And this will be in my third lecture. Thank you very much for your attention. Here, a question? Are there any questions? Are there any questions in Zoom? No. कोई मैसेज करके पूछा? Okay. No? Okay. So are there any quick questions? More questions you can ask outside because there's a class here. Are there any quick questions? Any quick questions? Please. Louder, please. On what point? Yeah. Yeah, it's not so easy. I mean, of course, you could think of this as something like an index theorem. Yeah, somehow you collect all the local indices of your vector field, and this gives Atiyah-Singer index formula something, a global invariant of your manifold. Yeah, but I mean, there are people like Christopher Denninger who have thought about this for a long time. And of course, it's tempting, but nobody has a convincing solution to this question. Yeah, so it's up to you to do it. So, oh, let's not discuss these technical questions now. We do this afterwards. That's the thing.
Any other quick question? If not, let's thank Professor Kings for a wonderful talk, and it was very exciting.
Thank you. Sure, sure.